classmates, I will be discussing about analytical equations for countercurrent stage contact. So a while ago, Mr. Lidora discussed about the mass balance of the mass balance involved in the gas absorption, and now we'll be discussing about more complicated and more complex equations. And so in order to do that, we must have assumptions. So in here, we will assume that vapor and liquid flow rates are constant. So with that assumption, the operating line equation will become straight. And also, the equilibrium line is also a straight line over the concentration range. Simplified analytical expressions can be derived for the number of equilibrium stages in a countercurrent stage process. So let's start the derivation. So first, we will be referring again to the overall component balance on A. So as discussed by Mr. Lidora a while ago, we have this equation. Then rearranging, it will become like this equation. Then another, we will be making a component balance for A on the first lowercase n stages. So we have this equation. Then next, we rearrange again that equation and we will have this equation. So as you notice, in this equation, on the left side, we have L dot x naught minus V1 y1, and on the previous slide, in this equation, on the right side, we have also L dot x naught minus V1 y1 minus V1 y1. So equating those equations, we have this. We will have this equation. Yes. So, but since the molar flow rates are constant, therefore L sub lowercase n and L sub uppercase n is just L, which is constant, and V sub lowercase n plus 1 is equal to V sub uppercase n plus 1, which is constant. So therefore, equation will become L times x sub n minus x sub n equals V times y sub n plus 1 minus y sub n plus 1. As you can see, we have lowercase n and also uppercase n. So the lowercase n is for the first stages, while the capital N is for the overall. So then, as we assumed a while ago, and as also I stated a while ago, our equilibrium line is a straight line, so therefore, y sub n plus 1 is just equal to mx sub n plus 1. And it's also with the uppercase case. Yeah. So substituting mx sub n plus 1 for y sub n plus 1 and calling A equals L over mv, we will have this equation where A is the absorption factor, which is always constant. So previous slide. So in this equation, all the factors on the right-hand side of the equation are constant. This equation is a linear first-order difference equation and can be solved by the calculus of finite difference methods. The final derived equations will be on the next slide. So for L to V or stripping, we have this equation and also this equation. It's a very complex equation, so I will not read it anymore. But if we assume that A is equal to 1, we will have this equation. There, we have that equation for stripping. Next. So for absorption, we have this equation and this equation. But for A equals 1, it will become like this. Pascal of absorption factor. Um, and so, the equations that you saw a while ago, they are called Kremser equations, and they are very convenient to use, but it has limitations. So it is only applicable if the units are consistent. If the units are consistent. So for example, if you have mass flow, then your x and y should be mass fraction, and if you have molar flow, then you should have mole fraction. So if A varies slightly from the inlet to the outlet, then the geometric average of the two values can be used. So again, how do we get the geometric average? So we just get the square root of the products of the two values. Next slide. And so for the sample problems, here is Mr. Leonard.
So, classmates, before we go to the sample problems, you might be wondering what is the equation for the operating line. So let me go back to the overall mass balance. From the multiple cascades, we have L naught plus Vn plus 1 equals Ln plus V1, being the strings equal to the mixing point. So for the component mass balance, we have L naught x naught plus Vn plus y, yn plus 1 equals Ln xn plus V1 y1 equals n xn. So if we are going to consider some stages or the first stages, say small n, we will arrive at the equation for the operating line like so. We will just solve for y plus 1 from the component mass balance. Okay, so this is the equation for the operating line. We have here the x component being the mole fraction of the desired component in the liquid, and y being the mole fraction of the desired component in the gas phase. From here we have Ln over Vn plus 1 is this. Okay, so we'll move on to the sample problem. And the problem goes like this.
For the first problem, it is desired to absorb 90% of the acetone in a gas containing 1 mole percent acetone in air in a countercurrent stage tower. The total inlet gas flow to the tower is 30 kg/moles per hour, and the total inlet of pure water to be used to absorb the acetone is 90 kg/moles per hour. The process is to operate isothermally at 300 Kelvin and a total pressure of 101.3 kPa. The equilibrium relation for the acetone in the gas-liquid mixture is Ya equals 2.53 Xa. Determine the number of theoretical stages required for this separation. Okay, so for the first problem, we will use the graphical solution in finding the total number of equilibrium stages. We are given the mole fraction Ya n plus 1 be 0.01, Xa naught equal to 0, Vn plus 1 30 kg/moles per hour, and L naught 90 kg/moles per hour. Okay. Making a total acetone balance within the system, we will first determine the amount of entering acetone. It is given by Ya n plus 1 times Vn plus 1. So that's about 0.01 times 30. And it is equal to 0.3 kg/moles per hour. Next, we will find the amount of acetone leaving with V1. So that's 0.1 times 0.3. That is equal to 0.03 kg/moles per hour. After that, we will calculate for the amount of acetone leaving with Ln. That is 0.9 times 0.3, and that's about 0.27 kg/moles per hour. And we will compute for the amount of entering air. That is quantity 1 minus Yan plus 1 times Vn plus 1. That's 1 minus 0.01 times 30. And it is equal to 29.7 kg/moles per hour. After that, we will compute for the flow streams. V1 is the vapor leaving the first stage. It is equal to 29.7 plus 0.03. So that's 29.73 kilogram moles of air plus acetone in 1 hour. If we compute the total number of moles in V1, it is equal to 0.03 over 29.73. And that's 0.00101. And we will compute Ln, the liquid entering the first stage. That is 90 plus 0.27. That's 90.27 kilogram moles of water plus acetone in 1 hour. If we compute for the mole fraction of acetone in Ln, it is just equal to 0.27 over 90.27. That's about 0.003. Next, for the operating line equation, since the flow of the liquid varies only slightly from L naught being 90 at the inlet to Ln being 90.27 at the outlet, and V from 30 to 29.73, the slope of the operating line, Ln over Vn plus 1 of the operating line is essentially constant. The operating line is plotted as well as the equilibrium relation Ya equals 2.53 xa. Starting with the point Ya1 xa0, the stages are drawn as shown. Yeah. Starting from the bottom, we will count the total number of equilibrium stages. And based from the graph, we have 5.2 equilibrium stages.
So much for the graphical method in obtaining the number of equilibrium stages. Here's Mr. Fernandez for the method.
Classmates, 안녕하세요. We have seen the graphical method. So how about the analytical method? We will be using the Kremser's equation for absorption. Mr. Kremser gave us this equation. And as you can see, the value for yn plus 1 and x naught are already given in the problem. While the value for the term y1 or y81 is can be easily obtained as had done by Mr. Serrano.